Okay, got 10 o'clock on my watch here. We're going to go ahead and get started. Appreciate everybody coming out to our first of our summer webinar series here at Calcium Products. My name is Andrew Hoiberg. I'm the oversee the research and development for Calcium Products here, along with the technical sales support. Along with me today, I've got Josh Enderson, who is one of our technical sales agronomists, and Glenn Howell, who is our other technical sales agronomist. They'll be here to help provide a little bit of color on some of the slides and also help to answer any questions that might pop up. We do have the Q&A thing enabled here on the webinar this morning, so if you've got questions or comments, please feel free to type anything into that. I just made a post on there to kind of show you where it's at, so you can also enter them into the chat too, but the Q&A would be the preferred spot to do that. So without any further ado, we'll go ahead and get started here. We've got this scheduled for a half hour this morning, but we may run a little bit longer than that, kind of depending on how things go. This is being recorded, so we'll try and get this put up to YouTube here after we get done today, and then we'll get this posted up to YouTube also for future reference as well. So thanks again for coming. We'll go ahead and get started here. So we've got four main topics that we're going to cover today, and the first, of course, is just kind of a background on what is soil pH. The second is, why is it so important? Why do we care about it? Which are things that I think most of you probably already know, but it's always good to kind of go back and get a refresher on some of that. And then also looking at, what type of things influence and affect soil pH. And then we'll finish up with some information about liming materials and different liming rates. So starting off here, looking at soil pH just from kind of the 30,000 foot view, and also including some information about how we look at it from a laboratory standpoint. Soil pH is, from a very simple standpoint, a measure of the hydrogen ions that are in the soil solution. It's represented as a negative logarithmic expression of that hydrogen ion concentration in the soil. That's not really something you have to remember, but when we think about a logarithmic scale, the thing you should remember is that going from a pH of 5 to 6, or from 6 down to 5, represents a change that's a whole order of magnitude different from the previous value. So just a change of 1 unit on the pH scale is a very significant number in terms of the difference in that hydrogen ion concentration. So, even though half a unit or a quarter of a unit might not seem like a big deal when you're looking at it on a soil test, just remember that that's representing a much bigger value than just the 0.25 or the 0.5 we're looking at. So in terms of how that affects agronomic values or nutrient availability or things like that, that's a really big deal when we're looking at that type of a number. So the way that this gets measured in the laboratory when they send it in is that a certain subsample of soil is going to be taken out of that soil sample that you send in. Generally speaking, only around 10 grams or so of that soil sample, which usually is about a pound or even more in some cases. Just 10 grams of that soil is going to get subsampled and evaluated for soil pH. So we're really looking at a very small amount of that soil that comes out of that soil sample, which then of course comes out of a much bigger 2.5 or 5 acre grid, or however tight you're doing those samples. What happens is they take that soil and they add the same volume of water to that soil. So if you got 10 grams of soil, you're going to add 10 milliliters of water to that. And that's what's shown here. Hang on just a second here. So right here, you can see that the water and the soil are the two things that are going to get mixed together first, and then a probe is put into that after it's agitated for a certain amount of time, and then that is going to be what shows you your soil pH value. The second thing they're going to do after they measure that is add a buffering solution. So when we see a soil test that's got the soil pH, or the water pH as it's called on certain soil tests, that's going to represent these first two things that we mix together. So the water and the soil, that's going to give us our pH value. That's going to kind of give us a snapshot of what we call the active acidification in that soil. So that gives us an idea of, how acidic is it and how much is that influencing things like nutrient availability. When they add the buffering solution, what they're trying to do is see, how buffered is that soil pH against pH change? So if we've got, a water and soil pH measurement of 4.0, to say it's very acidic, we add the buffering solution and it raises it all the way up to 7. That tells us that the buffering capacity of that soil is pretty low. And so that buffering solution is trying to raise the pH of that water and soil mixture, and the degree to which that succeeds tells us a lot about how much additional acidity is in that soil. If it succeeds in raising it pretty easily, that tells us we don't need a whole lot of extra liming material to change the pH. But if it only takes that 4.0 pH up to, let's say, 5, that tells us that we've got a lot of work to do, a lot of reserve acidity in that soil and a very high buffering capacity. We'll talk more about that on the next slide as well. But again, just to kind of summarize what we're seeing here is these first two things, the water and the soil, give us that measurement of the soil pH, which again tells us, do we have a problem? And again, expanding on that to the buffering capacity, and I wanted to explain that in the previous slide because we've got that graphical image there that shows you how that's measured in the laboratory. So again, we're looking here, when we look at the buffer pH, there's a lot of confusion when growers or even some agronomists look at this value. They say, what the heck is that buffer pH value and what's it trying to tell us? And again, it's trying to tell us how buffered is that soil against pH change. And again, if that buffering agent only brings, if those two numbers are pretty close, let's say within a unit or so of pH, if it's acidic, that means that it's probably going to need a fairly large amount of liming material to correct that soil pH. So again, this is looking at the reserve acidity, all the stuff that's kind of connected to the soil that doesn't show up in that initial soil pH measurement. But we can kind of think about this with an analogy between two different tires. So if we've got these two tires that are representing different soil types, the bicycle tire would be representative of a low CEC soil, coarse textured, sandy textured soil that has a low buffering capacity. If we look at the tractor tire, that's one that's got a lot of organic matter, a lot of clay in it, a real dark, dense soil that has a very large buffering capacity. It can hold on to a lot of acidification. And if we look at the amount of liming material, or in this analogy, the air that's needed to inflate these tires, let's just say that they're both at 40 psi, or analogous to our 4.0 soil pH measurement, and we need to take those up to 5.0 or 50 pounds of pressure. It doesn't take very much air to put that bicycle tire from 40 to 50 psi. From this tractor tire to go from 40 to 50 psi, it's going to require a much larger volume of air to do that. And so we can kind of think about, two different types of soil in that way. Again, the lower CEC one and the higher CEC one in terms of buffering capacity. And that's really what that buffer pH measurement is trying to tell us. And the only practical, you can't look at it and say, other than knowing if it's close together or far apart, you can't really look at it and say, with any certainty what you need to put out for a liming rate. That number is used in pretty advanced equations that are used to determine the liming rate, and we'll talk more about that later. So again, you just need to know that buffer pH measurement is there to help us calculate exactly this bullet point right in the middle, the lime requirement of the soil. Soil pH is considered a master variable when we look at the different types of characteristics that are in soils, and from a soil science standpoint, we consider it a master variable because it governs all the different processes in the soil. So the things that kind of come together to promote soil quality and soil health, and to really help get a crop from emergence all the way to a good harvest and help support it along the way. All those different things that happen, the physical, the chemical, the biological things that are taking place there, are all governed by the soil pH in one way, shape, or form. So the biggest one that we tend to put a lot of focus on is the availability of the essential and non-essential nutrients. And why would we focus on the non-essential nutrients? Because when you think of things like aluminum is not a nutrient that's considered essential to plants, but soil pH, once it gets down below a certain threshold, aluminum starts to become a lot more available in the soil, and what that creates is a very toxic environment for the plant. So those non-essential nutrients, again, are not ones that are required for plant physiology or yield maximization or anything like that. But if they become in a situation where you're too acidic, and then aluminum starts to come out into solution, that's going to affect the plant in a negative manner. And so that's one of the things that cause things like club rooting when you have low soil pH. Activity of all the microorganisms, again, both good and bad, are going to be affected by soil pH. So if we've got soil pH out of whack, we don't have those microorganisms that are in there promoting the nitrogen cycle, the sulfur cycle, the phosphorus and potassium cycles, all those things that the microorganisms are responsible for in the soil. If they're out of whack in terms of soil pH, are not going to help promote that nutrient cycling like we need to have healthy crops. Ability of the soil to hold on to cations. So if we look at soil pH that gets low, a lot of times you'll see on your soil test you've got large number of hydrogen ions. Of course, we talked about that. And what that does is it can artificially reduce the amount of calcium or magnesium that the soils can hang on to. And so you look at your soil test and you think, well, I'm right in the heart of the Midwest. I should have plenty of calcium in my soil, but this base saturation is showing me that I only have 50% calcium in there. Well, that's largely going to be driven by the amount of hydrogen that's in that soil. Soils have a characteristic called preferential adsorption. And what happens is when soils are overwhelmed with hydrogen, they want to try and hold on to that. And so that suppresses the amount of calcium and magnesium that soils are able to hold on to. And again, will be influenced by the acidity of the soil. Herbicide performance, expression of genetic potential, all these types of things are very important things that are governed by soil pH. So we kind of drill this down to the three main things that are really going to help affect that crop health and the ultimate yield that comes out of that crop. Yield potential, nutrient availability, and biological activity. These three things are all very, tightly interconnected, and it all kind of hinges on that nutrient availability for the yield potential. But that nutrient availability is always also very reliant on biological activity, like I mentioned in the previous slide. So when we look at the yield potential graph first, you can see, this kind of gives us some information about the relative average yield of a variety of different crops here at varying soil pH ranges. And you can see, it's not until we get up around 6.8 that we get that relative average yield at 100% or close to it. A lot of target pH values in the Midwest are set right around 6, and I know the conventional wisdom tells us that we should be right around 7. But really, when it boils down to should we manage soil pH to 6 or should we manage it to 7, like we've kind of historically been taught, we're looking at two different heads of this kind of this twofold problem. If we manage it to a pH of 7, we're going to spend more money on the liming materials, and we might not get that little extra, yield increase. Like if we look at some of these crops here, you might see a 20% difference average in yield. And, some of this is textbook, but if we had one right in between the middle here that was right at 6 or 6.2, that would be the area that we would really want to manage to, because the amount of additional money you're going to spend to take it all the way up to 7 is not going to account for the additional increase in yield that you'll get there. So most of the Midwestern universities, Iowa State, Wisconsin, Minnesota, Nebraska, South Dakota State, North Dakota State as well, all those universities are promoting a soil pH, generally speaking, of between 6 and 6.5 for corn and soybeans. So the days of us needing to manage it to 7 are behind us. Of course, that's different for things like alfalfa, but when we're talking about corn and soybeans, you really are fine managing that pH to 6 or just a little bit above that. And again, the other big driver of all these relative yield numbers is going to be this nutrient availability. And I know there's a lot of different lines and colors and things on this graph, but the two main things to kind of focus on here are this one that we've got highlighted in red, which would be the phosphorus availability curve. You can see that as you start to get below 5.5, below 6.5, you can start to see that phosphorus availability declines pretty rapidly. So again, that sweet spot going to be between 6 and 6.5. Once you get above 6.5, that pH scale tends to affect phosphorus as it wants to tie up with things like calcium and magnesium. As you get below that, it wants to tie up with things like iron. So phosphorus, as we all know, is a very reactive nutrient in the soil. It likes to, react with a lot of different cations and things in the soil. So again, promoting that that soil pH right in where it should be really helps to promote that phosphorus availability. That's the biggest one when we look at nutrient availability. Phosphorus is the one. And this reminds me, while we're talking about this, that we've heard some people say, because phosphorus application rates are going down, because we're not doing as much with those due to the farm economy this year, therefore we don't need to worry so much about soil pH. And that's incorrect thinking for two reasons. The first is we still have a lot of phosphorus in the soil, so we want to be able to take advantage of what's in there. Just because we didn't apply phosphorus doesn't mean that we don't have to still manage our soil pH for that. The other one that we'll talk about more here in a minute is that the thinking that phosphorus is the type of fertilizer that's causing lowering pH is partially correct, but it's not completely correct. We're getting a lot more acidification from the other nitrogen sources we're using, not just MAP or DAP, and we'll talk more about that as we get there. But to think that because we're not applying as much phosphorus due to the farm economy, meaning we shouldn't worry about soil pH is incorrect thinking, and we absolutely should be worrying about that soil pH even when we're applying less of that, because at the end of the day, we're still applying a lot of nitrogen, and that's the biggest driver of soil acidification. The other thing to point out here, we talked about it earlier, is the aluminum. That's going to be this one here. As we get below a soil pH of 6.0, that availability of aluminum just skyrockets, and that's really where we get into that toxic environment where the plant has to, by force, take some of that up and end up with a club root type of a situation. There are other things besides fertilizer application that can affect soil pH, but in terms of the magnitude in which these things affect soil pH, these are not even close to what nitrogen application does. But they should be mentioned because they're important as a whole, nonetheless. So, things like, again, this conversion of ammonium, which we'll focus more on in the next one, we'll highlight that. Oxidation of elemental sulfur. So that is another way, and there's a little bit of confusion in terms of the sulfur contribution to acidification. We've got elemental sulfur on one hand, which as that elemental sulfur oxidizes to sulfate, that's what creates the acidity in the soil. Other types of sulfur don't acidify the soil like elemental sulfur does. When we look at things like ammonium sulfate, calcium sulfate, which is gypsum, ammonium thiosulfate's kind of in the middle. There is a little bit of acidification that comes from that. But sulfur sources that already have sulfate in their sulfur form do not acidify the soil from the sulfur side of things. That only happens, again, from that elemental oxidation or from a little bit of the thiosulfate phase change. Largely, when we're talking about ammonium sulfate acidification, that's strictly from the ammonium, not from the sulfur side of that. So that's an important thing to remember. Rainfall can also influence soil pH by leaching basic cations or calcium, magnesium out of there. Acid rain from atmospheric CO2 can also cause a little bit of acidification. Organic matter cycling can cause a little bit of acidification, but again, none of that, all of that pales in comparison to what we do from a nitrogen management standpoint. We've been talking about this for a long time. If you've seen us speak somewhere before, you probably have seen this graph, but when it comes down to it, kind of depends on your geography, of course, but in Iowa, we use a lot of anhydrous. And that anhydrous, just from a volume standpoint, is the biggest driver of soil acidification in our state. In other states around us where there's more urea or other types of fertilizers you see listed here used to contribute that nitrogen, they all kind of add up to the same effect. Some of them, like ammonium sulfate, is the most acidifying of the nitrogen sources, and that's from a chemical standpoint. Just because of how it's chemically set up, you get more hydrogen as part of that downstream reaction as that ammonium converts to nitrate. That's what acidifies the soil. So all these different nitrogen sources that contain some form of ammonium or ammonia in there, as that's converted into nitrate in the soil, that's what's creating the acidification. And again, when we think about MAP and DAP from a acidification standpoint, yes, they do acidify the soil, and it's sort of like the sulfur thing I just mentioned. It's not from the phosphate, it's from the ammonium that's in there. And so, if we're looking at lowering our MAP or our DAP application rates, that's one thing, but I would venture to guess that nitrogen is being made up somewhere up here with something else. If we're lowering our phosphorus application, we're going to make up for that nitrogen somewhere else. So that's still going to acidify the soil at the same rate, even though maybe we're lowering those phosphorus application rates a little bit. So again, we should still be very focused on what that soil pH is. And in these tighter economic times, one thing that we can really do something about and provide additional benefit with is to manage that soil pH to make sure that all the nutrients we are putting in are being available and for that crop to take up and maximize its yield. So this is a chart that we put together. Josh, maybe I'll kick it over to you to take these next couple of slides.
Yeah, you bet. Thanks, Andrew. So stemming off of that previous discussion we had on the last slide there, we put together this chart based on the amount of pure calcium carbonate of product or lime that's going to be needed to neutralize the full acidifying effects of the listed fertilizers you see there on the left-hand axis there. So what we did is we assumed that we're applying 100 pounds of each and every one of these products, except for the elemental sulfur. Obviously, nobody's going to apply 100 pounds per acre of elemental sulfur. You can see there the asterisk shows that the elemental sulfur number, that's based off of a 25 unit sulfur application. So actually, if we're using elemental sulfur to apply 25 units of sulfur to that crop, it's actually going to take 80 pounds of pure calcium carbonate to neutralize the acidification effects of that elemental sulfur once it completely oxidizes, breaks down, and turns into plant available sulfate sulfur. Same sort of principle applies to a lot of the nitrogen in all of these fertilizer sources you see on the left-hand side. This is assuming that all of that ammonium nitrate is converted into nitrate. So obviously, corn likes to take up ammonium as well. It can take up ammonium and nitrate. So it's not 100% going to have the chance to convert all the way to nitrogen, but this is just assuming that to kind of give you what might be or could be the worst case scenario based on, from an acidification standpoint, based on a 100-pound application of these products. Like Andrew mentioned with MAP and DAP, all of that acidification is coming from the ammonium in monoammonium or diammonium phosphate forms. Next, we kind of applied the same sort of principle to some of the liquid fertilizers. So on the top there, you have a lot of what would typically be used as starter fertilizer or in-furrow type of products in corn production. So you can see those are basically driven off of the nitrogen amounts in those fertilizers. That's why you see the 624-6, that's going to offer a little bit lower nitrogen from a percentage basis, so it's not going to acidify as much per gallon of volume applied. Next, you have your typical UAN 28 and 32%, same sort of principle there. And then finally ATS. So ATS, as it's become more popular, Andrew mentioned earlier, when it comes to sulfur, there's kind of sulfur in a couple different forms within ammonium thiosulfate. And so not only are you getting acidification from the ammonium, but one of the two forms of the sulfur in ammonium thiosulfate is going to contribute to that acidifying effect as well.
Great, thanks, Josh. So we kind of focus back here on the next part of the presentation here, looking at different liming materials. There are several different options around there. Primarily, of course, you have agricultural lime or ag lime, but you also have a variety of different waste byproduct type liming materials, such as beet sugar lime, also water treatment lime that we can see coming out of various places, and then pelletized limestone like we make here at Calcium Products. There's pros and cons to each one of them. We'll talk a little bit about that as we go along here. So when we look at, the way that limestone works, or lime, whatever the liming material is, the basic kind of chemical steps are that you add calcium carbonate into an area that has free hydrogen. And what's happening is that hydrogen, again, is what creates the acidification. So in order for calcium carbonate to dissolve or to become soluble in a soil solution, there has to be acidity. So if you put calcium carbonate out on a non-acid soil, it's just going to sit there as calcium carbonate. You're not going to get benefit from the calcium. You're not going to get benefit from the carbonate because there's nothing in there to help dissolve it. So inherently, limestone is a very insoluble material. I think the solubility, if you took a grain of limestone the size of the head of a pen or a pin and put that into a gallon of water, you'd be able to get that to dissolve, but that's about it. So it's, again, needs acidification in order to dissolve and liberate that calcium and the carbonate away from each other so that that carbonate is able to react with the hydrogen, which then creates H2O, water, and also carbon dioxide. So if you think back to your, well, we'll talk about this in a minute. I won't get ahead of myself. And then you've got the calcium that's liberated also to help with, soil amending benefits or all the great things that calcium does in the soil. When we look at how liming materials are compared against one another, they're all compared against pure calcium carbonate. And when you see on a limestone analysis report, this term, the CCE, what that is short for is the calcium carbonate equivalent. And what that is, it's a chemical titration that looks at the parent material or that liming material and determines what the quality or the purity of it is. When we talk about limestone, it comes in two basic varieties, one being calcitic and one being dolomitic. The difference between those two is the amount of magnesium carbonate that's found in only dolomitic limestones. Now, it doesn't mean that the dolomitic limestones are 100% magnesium carbonate. There's still a majority of calcium carbonate, but they have some percentage, usually greater than about 5% magnesium in them, is where that cutoff line tends to be. It's a bit of a gray, fuzzy area, but around 5% or more of magnesium tends to be considered a dolomitic limestone. So we tend to see dolomitic limestones in eastern Iowa and then up into Wisconsin and then into Illinois as well. That doesn't mean that's the only place we find them. You can see them in other spots as well. A lot of that is governed by how the parent material was formed thousands and thousands and millions of years ago. But calcitic, generally speaking, is a lot more effective than dolomitic is, even though dolomitic looks better on paper. So when we look at a pound of dolomitic limestone versus a pound of calcitic limestone, the dolomitic on paper, gets a more of a neutralizing value because of the magnesium carbonate that's in there. Magnesium has a lower molecular weight than calcium does, and so pound for pound, you get more carbonates with magnesium carbonate than you do with calcium carbonate because of that molecular weight difference. Now, that difference on paper does not equate to effectiveness in the field. Calcitic limestones are always more effective and don't require as much material as dolomitic limestones do to achieve the same pH change. So don't let that difference on paper fool you. States will then put this information into a formula. Generally, it's the moisture content, the fineness of the material, and then the purity or the CCE value. And that's what we get these different scoring systems from in different states. They're all trying to tell us the same thing. Their equations and their methods are just a little bit different from each other. So you can look over here, for example, to see how our 98G pelletized limestone looks on different state scoring systems. So you can see it's, generally the numbers are around the same depending on how they grade it, but all those numbers are trying to tell us is if we have liming material A and liming material B, how can we compare the two of those? Turns out these state systems don't do a very good job of comparing, especially our material against others, but we've got our own equations and stuff to account for that. Looking at water treatment and beet sugar lime, these materials are very dependent on A, the feedstock of limestone that goes into the process, and B, the actual process itself, which makes these byproducts. They almost always have a high moisture content, so they're difficult to apply. You can see how sludgy these materials look in these pictures. They also can be very finely grained, so once they do dry out, it's hard to spread them effectively, so you are kind of hit on both sides of wet and clumpy versus dry and powdery, making them difficult to spread in either scenario. They also will have very low purity, can have very low purity, and then once you factor in the moisture content, it makes the effective purity very low. Also, they oftentimes contain heavy metals and impurities. So you can see aluminum is the one that we oftentimes see in the water treatment and beet sugar limes. That's also an addition to, from the process standpoint, that gets added into these materials that ends up in the byproduct. We talked about how bad aluminum is for crops earlier in the presentation. So the last thing we want to do is apply aluminum out onto the field with these byproduct materials. So again, they're usually free for a reason because the plants want to get rid of them. Or very low cost, not always free, but low cost. So you're paying to ship a lot of water, and you're also paying for things that we don't really want to put out onto the field, like aluminum. So just be cautious with those types of materials. Typical ag lime analysis. So this is generally where the state shows us what the effectiveness of a limestone is between the 4 and the 60 mesh. Mostly 98G is going to be made up of 60 plus mesh, the superfine material, which is very good at changing the soil pH. These coarser materials are not as good at changing the soil pH. And so we've built these stacks of a lot of different ag limes in the Midwest to help illustrate the differences or the inefficiencies that are built in with agricultural liming materials. We'll talk a little bit more about that on this one. So when we look at the effectiveness by particle size, if you look at the effectiveness within 1 year of application, you can see that 8 mesh and above is going to be 5% or less. Between 8 and 30 mesh, only about 20% available. Between 30 and 60, you're getting closer to 50%, and then 60 or smaller, you've got closer to 100% availability. And so that's why most states stop at the 60%. There has been some research that has shown that even the 60 mesh particles are not quite as available as we thought they once were, but certainly there's some additional benefit from having these finer particles that it's not accounted for in those state scoring systems. And that's why we have our own proprietary equations for these materials. Effectiveness after 4 years, so kind of a traditional liming program. Looking at a 4-year application, you can see that the numbers go up, but are still very low for the up to the 30 mesh materials. So when we look at this, we tend to think of comparing ag lime to 98G, and we're not really comparing apples to apples. It's apples to oranges, because a lot of this material that still gets credit from the state scoring system is too coarse and ineffective to change the pH of the soil. You can see in this particular example, that's almost 50% of that ag lime volume is going to be ineffective at changing the pH. 11% is going to be good and reactive and have minimal drift when you spread it. And then this additional 40% down here is very reactive, but also very vulnerable to drift loss. We worked with the USDA a number of years ago to quantify how much of that material is going to be lost off target when we apply it. So you can see even on a general, I would say with pretty good certainty that the wind has been getting worse in the last 10 years. And I think there's some good data to back that up. But, on a kind of normal 10 to 15 mile an hour windy day, we could be losing up to 25% of that finest material is going to be drifting off target. So this 40%, we need to subtract out over half of that now that's going to drift off target. And so that's really, you put together this picture of 2 coarse particles, 2 fine particles, and now we start to see why there's such big application differences between 98G and ag lime. If you're interested in learning more about the ag lime that you've got in your area, this is a map that we've created on our website. You can go click on the 98G challenge area of the website, and you'll be able to get to this map. And each one of these dots represents a different limestone, generally a quarry. Some of them are field piles, but mostly quarries that we've sampled over the years. You can see we've got a really high density in the Midwest of these samples that we've taken. If you click on any one of these dots, it's going to give you this little box of information over here that will tell you, some different chemical and physical characteristics of that. We've also got links down here to look at that ag lime stack picture, so that'll show you one of these of that. If we've got it, we didn't start doing that right away when we did these, but we've got it for most of these. And then also another link down here to look at the lab analysis that gives you the full particle size breakdown and the chemical breakdown of that ag lime. So there's a lot of great information here if you want to get a little bit closer to your own backyard and look at what's available And the other thing to note here is how 98G compares to those materials. People often ask us if we have a recommendation that calls for a ton of ag lime, how much 98G do we need? That's really hard to say with a general statement. So we've got that here to show you a general number. Now, we would always want to have a computed application rate for 98G. Wouldn't want to just go off of what your ag lime recommendation is, but this gives you kind of a starting place for what that difference looks like. So focusing a little bit more on 98G here, it's made from 98% pure calcitic limestone. So again, that calcitic is going to offer us quicker reactivity and overall better effectiveness compared to dolomitic. We then put it through our proprietary grinding process to get 90% of it passing a 100 mesh sieve. Again, that really helps to drive that rapid reactivity that 98G has become known for over the years. We pelletize it in our system, which is called a pan agglomerator. It's basically a big pan that spins around. We have material that gets dumped into it, combined with our binding agent, and then creates pellets that get thrown off the pan once they reach a certain mass. Then they go through the drying and screening process, and then on into our storage bins. What we're left with 98G is very effective and efficient correction and maintenance of soil pH. We talk a lot about pH correction, and we as a company have started talking a lot more about soil pH maintenance, but the idea behind the maintenance is really to offset that acidification that we put out there every year with our nitrogen management, or to keep the pH level and prevent it from going through the kind of roller coaster of peaks and valleys that we tend to see with pH over time when we only manage it in 4 to 5 year windows. When we compare ourselves to other pelletized limestones, I know I just got done bashing the state scoring systems, but when we look at pelletized limestones, the state scoring systems are really all we have to look at the differences here. And since these materials are more closely related than looking at an ag lime versus a pelletized lime, we can use that scoring system with a little bit better certainty here when we're comparing these types of materials. So 98G, again, has the best purity out of all these materials. You can see that represented in the calcium carbonate equivalence number. Also has the best effective calcium carbonate number, and again, that combines the fineness, the moisture content, and the purity of the material. So you can see that when we're looking at some of these various other materials that are available in the Midwest, we've got somewhere between a 10 and a 20% increase in that effective calcium carbonate equivalence. And so what that translates to is a lower application rate with 98G when we compare it to the other ones. So even if cost is a little bit lower for some of those other materials, when you factor in that additional material you need to achieve the same type of performance, 98G will often come in at the same price or even a little bit lower once we factor in those application rates. We also have these pounds equivalent things down here, and what that does is it factors in the magnesium value. So again, if we look at magnesium being something that slows down the reaction and requires more material to get put out, that's why you see that big difference here in the application rate, especially for this one particular pelletized limestone. This information is all available on that limestone map that I showed earlier as well. So we've got the kind of classic equation GIF here to help illustrate some of the work we've done. These are Iowa State's equations that you see over here. And when we talked about, buffer pH and soil pH, there are some sets of equations that take into account the buffer pH only, like Iowa State's does, and then also some states like Wisconsin that take into account both the soil pH and the buffer pH. We use a hybrid approach between the two. We do use both soil pH and buffer pH. We've got our own rate calculation equations that are available through a lot of the top VR software platforms that are out there. So the chances are that we've got those equations available to you. You might not know that they're available to you, but if you don't have those, please feel free to reach out to myself or Glenn or Josh, and we can get you set up with those equations. We also have a rate calculator on our website that you can go to kind of get a quick estimate of what that application rate needs to be. So here's a video that I want to show. Hopefully I can get it to run here.
Andrew, I think if you just click like you're advancing the slide, it should start.
Oh, there you go. Thank you. So these are vinegar-filled cups, and this is a ag lime that's got some fineness to it, and so you're seeing a little bit of that reactivity, that CO2 evolution like we talked about earlier, but you see a quick die down from that too. So those coarse particles are left in there to kind of take over, and you just won't see much activity from those. This next one is a competitive limestone that we're putting in there, a competitive pelletized limestone. And again, you see more contribution, more fast reactivity from those fine particles that are in there, but then 98G, you can really see the effect of purity, particle size, and then the precision aspect of it too. With these pellets are getting in there and breaking down super rapidly and releasing that calcium carbonate into solution into that vinegar solution to then neutralize the acidification that's in there. And so, this notion that 98G is renter's lime or a quick acting limestone, it's true, that does happen. But the other part of that is you also see a more sustained reaction on the acidification neutralization than you do compared to ag lime. And so thinking of ag lime as kind of a slow release or extended release type of liming agent is again true, but the reality of that is that you're never fully attacking that full pH problem by using ag lime, unless you're using it at a ridiculously high rate. Because I have a suspicion that for the last 40 or 50 years we've been applying ag lime at far too low of a rate to actually achieve the type of pH correction that we need to have in soils. And that's why we hear from a lot of people from time after time saying we put out ag lime, we came back and checked the soil pH a year or even 2 years later, there wasn't any change, or it went back down in soil pH. So we didn't really get any effectiveness. So I think what we've kind of created in agriculture is a much bigger soil pH problem than we're even fully aware of. And so when we go out and put these liming applications out, we're doing good. It's we kind of refer to it as a leap of faith sometimes, because even if we don't see a big change in those numbers, anytime we put a liming material out there, we're going to be offsetting some of that, even if it's just the active acidification. Remember, we've still got that reserve acidification kind of waiting to come, get put into the soil solution after we take care of the active acidification. So, again, just know that you're doing some good out there, but also know that this is a bigger problem than I think we really realize, and really need to be more proactive about how we approach that and how we manage it. And so again, 98G really presents a great opportunity for us to go out and not only correct, but also maintain that soil pH. So if we can get out there, and look at some of our research results, which are available on our website, we'll talk more about those on Thursday in the second part of this. And when we kind of dial into the economics of soil pH, we'll have more information about that. But we really are seeing a nice close to a 10 bushel increase on just using a 250 pound 98G application to help promote some of that active acidification being neutralized and helping the plant to access those nutrients in the season of application. So again, we're talk a lot about tight farm economy and not wanting to spend a lot of additional dollars per acre, which I totally get. But that 98G application of 250 pounds can be done for a relatively low cost, and really can help promote better crop uptake, better nutrient utilization, and ultimately better yield. So I know we've gone a little bit over the time here today, so I don't see any questions in the chat, but we are going to do this particular one again next Tuesday, but would like to see everybody on Thursday when we expand on this and talk more about the economics of soil pH and how it really costs dollars and cents for growers. So appreciate everyone's time. We'll stick around here for a few minutes. If there are any questions, people are welcome to stay. But if not, we wish you a great rest of your Tuesday, and we'll hope to see you all on Thursday. Take care.